The distribution of sample proportions will be considered nearly normal when the distribution is not too strongly skewed for its sample size. For example, on the graph on the left, we're going to this was built with the probability of success being 0.9 and with using samples of size 20. And if you compare that graph to a normal distribution, you can see it doesn't fit very well. And that is, when the probability is 0.9, a sample size of 20 is just too small. On the other hand, for samples of 200, it's not perfect, but you can see that it matches a lot more to the normal distribution. So in this case, a sample size of 200 looks like it would be a large enough sample. So specifically, the sampling distribution for sample proportions taken from a sample of size n from a population of true proportion p, where p is, again, the probability of success, we'll consider that nearly normal when, first, the observations are independent, and by that I mean a random sample from less than 10% of the population, and we expect to see at least 10 successes and 10 failures in our sample. So, in formula mode, we want n times p to be greater than or equal to 10, and n times 1 minus p to be greater than or equal to 10. When the true proportion is not known, or we don't have any guess for it, we'll use the point estimate, the sample proportion p hat, in its place. Alright, so for example, which of these samples would be considered large enough based on that n times p, n times 1 minus p? So, a sample of size 20, where the probability of success is 0.5, well, the number of successes in this case would be n times p, or 20 times 0.5, which is 10. The number of failures, n times 1 minus p, or 20 times 1 minus 0.5, is also 10. So we have at least 10 successes, at least 10 failures. In this case, we would consider the sample size to be large enough. Suppose the sample size was 100, so technically a much larger sample, but the probability of success is a lot lower at 0.05. Well, the number of successes, 100 times 0.05, put that in our calculator, 100 times 0.05 comes out to be 5. And right away we know that we don't have enough successes here. Number of failures, on the other hand, 100 times 1 minus 0.05 comes out to be 95. We definitely have enough failures, but overall there are not enough successes, so we're not going to be able to use the central limit theorem. We're not going to be able to use the normal distribution. If the sample is size 30 and probability of success 0.7, well, 30 times 0.7 is 21. 30 times 1 minus 0.7, 30 times 0.3 is 9. Not quite enough. I mean, probably isn't going to be too bad, but we don't quite have enough failures in this case. So we would want a little bit larger sample. If the sample size is 35, probability 0.4, well, 35 times 0.4 is 14. 35 times 1 minus 0.4, 35 times 0.6 is 21. We do have at least 10 of each, so the sample size is large enough. So, this is not quite technically the sample size itself, but it's the number of successes and failures you also have to keep in mind.